A pleasant day, everyone. I am Jolly Grace R. Castro from BSc 3B Mathematics. So for today, we are going to talk about Wilson's theorem. So what is Wilson's theorem? Well, basically, Wilson's theorem is a test to see whether a particular number which is greater than 1 is prime or not. Wilson's theorem says that a natural number p is greater than 1 is prime if and only if p minus 1 factorial is congruent to negative 1 mod p. If this condition holds true, then the number that you have which has greater than 1 is prime. First, let's define factorial. The factorial of a positive integer p is the product of all the positive integers that are less than or equal to p. Now let's have an example. Suppose we have p is equal to 5. If you want to see whether p is a prime or not using Wilson's theorem, all you have to do is to see if this particular formula holds true. So let's see if p minus 1 factorial, in this case p is equal to 5, is congruent to negative 1 mod 5. So p minus 1 factorial is equal to 5 minus 1 factorial, which is 4 factorial, which is equal to 24. Because 4 factorial is 4 times 3 times 2 times 1. 4 times 3 is equal to 12, 12 times 2 is equal to 24, and 24 times 1 is equal to 24. So p factorial, in this case 5 minus 1 factorial, is equal to 4 factorial, which is equal to 24, and 24 mod 5 is equal to 4, and as you know, is equal to negative 1 mod 5. And if you don't know why 4 is equal to negative 1 mod 5, we talk about how to find mod in a particular number, especially if you have a negative number. So if you have a negative number, all you have to do is you will add your p, in this case is 5, to the negative number until you reach a number which is between 0 and your p, which is 5. So if you have negative 1, if you add p to it, which is 5, negative 1 plus 5 is equal to 4. Therefore, 4 and negative 1 are equal in mod 5. So Wilson's theorem is a great tool or test to see whether a number that is greater than 1 is prime or not. Now, let's proceed to discuss the proof of this theorem, which is called Wilson's theorem. Wilson's theorem says that if p is a prime number, then p minus 1 factorial is congruent to negative 1 mod p. To show that this is true, let's first expand out the left-hand side up. This p minus 1 factorial, if you write it out in full, it's p minus 1 times p minus 2 on and on times 3 times 2 times 1. The strategy is to pair each number with its inverse. And because we're working mod p, the integer mod p are a field, which means other than 0, you can't divide by 0. So every non-zero number mod p has an inverse. So we should conceivably be able to pair every number with its inverse. But there are a few exceptions, and the exceptions are there are some numbers that have their own inverse. So let's see which ones those are. If a number has its own inverse, that means it's a solution to x squared is congruent to 1 mod p. Because x times itself x squared, it gives you 1. Now we can solve this congruence. Let's just subtract 1 from both sides, and that gives us x squared minus 1 is congruent to 0 mod p. Now we factor, that gives us x minus 1 times x plus 1 is congruent to 0 mod p. Now we just solve this like we would in algebra. So now we just set each factor equal to 0. So if x minus 1 is congruent to 0 mod p, means that x is congruent to 1 mod p. So 1 is its own inverse. Next, x plus 1 is congruent to 0 mod p. If we have to solve this, we get x is congruent to negative 1 mod p. Next is x plus 1 is congruent to 0 mod p. If we solve this, we get x is congruent to negative 1 mod p. Or to write it alternatively, you can write this as x is congruent to p minus 1 mod p. So 1 and p minus 1 are their own inverse, but every other number mod p can be paired with this inverse and it'll be different number. So now let's go back to p minus 1 factorial. So let's take in group 2 with its inverse. Let's group 3 with its inverse, and so forth. We'll be able to do every number, and the exception being 1 and p minus 1. Now 2 times its inverse is 1, 3 times its inverse is 1, and so everything can be cancelled out. And what we're left with is p minus 1, which as we solved just above is the same thing as 1 mod p. And this proves that p minus 1 factorial is congruent to negative 1 mod p. That's all for today. Thank you for listening.